In this video, we investigate non-homogeneous systems of linear equations with infinite solutions. So let AX equals B be a non-homogeneous system. We're writing it as a matrix equation, not a system, but we've seen that systems, matrix equations, and vector equations are the same thing. So, theorem. Let AX equals B be consistent, i.e., assume it has at least one solution. The solution set turns out to be related to the solution set of a related homogeneous equation. So we know from earlier work that if we replace this B with the zero vector, AX equals 0, it has as its solution set a linear combination of vectors, one for each free variable. And now let P be any solution to AX equals B, i.e., A times P equals B. P stands for particular solution, and the solution set to AX equals B is gotten by combining these. The solution set to AX equals B is any particular solution plus the solution set of the associated homogeneous system. This theorem is always true, but it's only interesting if there are infinite solutions. If the consistent system has one solution, it turns out that the associated homogeneous system also has only one solution, the trivial solution, and this theorem becomes the very uninteresting statement that the single solution P equals that same solution plus the zero vector. We saw something very similar to this in differential equations if you've taken that course. If you haven't, this is the last section where I'll keep referring to it, so don't worry. But in differential equations, we have a basically identical theorem for non-homogeneous linear differential equations. This theorem is a lot more theoretical, as it were. In differential equations, the corresponding theorem is really a solution finding technique. We don't have a general method for solving non-homogeneous equations, but we can solve homogeneous equations, find a particular solution using a computer, for example, and then we have a general solution. Here we don't need a theorem to help us find solutions. We already have Gauss-Jordan elimination. This is going to be much clearer if we look at an example. Let's solve the following non-homogeneous system. So we'll use Gauss-Jordan elimination. We won't at this point refer back to the theorem. We'll just write down the augmented matrix. And we put it in reduced row echelon form. And I am, as usual, not showing the individual steps in the elimination process. You should just be doing this on your calculators by this point. But we get the following. And we'll now repeat the process we used to write the solutions of a homogeneous system. The basic variables are x and y, because these are the pivot positions, while z is free. We write the equations from the first row, from the second row, and a useless equation we don't bother writing down, that 0 equals 0. We solve for the free variables. The free variable y is already solved for. And we add in an equation. Sorry, I think I just misspoke. We solve for the basic variables. X is basic, y is basic. Now we add in an equation for the free variable z. we buffer the right-hand side with zeros. And now we can turn this into a statement about vectors. So the vector x, y, z equals this vector plus z times this vector. You see a difference between this and the homogeneous case. In the homogeneous case, all the vectors that appear are being multiplied by a free variable, like this. Only in the non-homogeneous case do we have a vector by itself, not multiplied by anything. Our solution is in two parts. Let's go back to the theorem. The solution to this is supposed to have the following form. It should be a solution to this system, a particular solution, plus the solution set of this corresponding homogeneous linear system. We can verify that this is the case. Plug these numbers into this system, and we get three true statements. So this really does represent a solution to this system. This infinite set of vectors is supposed to be the solution set of the associated homogeneous system. Verifying this requires a bit more effort, but if we solve the homogeneous system, we do get this. So start with the homogeneous system. Set up the augmented matrix. Perform Gauss-Jordan elimination. Write down the new system. Solve for the dependent variables and write in an equation for the independent variables. And then rewrite that as a vector. And if we compare this to this, they are the same. So this is the solution to this homogeneous system. system. Of course, we didn't use the theorem to solve the system. I mean, we didn't first solve the homogeneous system, then find a particular solution, then put them together. Instead, we used Gauss-Jordan elimination, and then the result of the theorem simply fell out of it. In this video, we saw how a theorem of differential equations has a parallel result in linear algebra. When we get to vector spaces and linear transformations, we'll see why we often see the same theorem repeated in seemingly different contexts like this. And there's a practical as well as theoretical take-home message here, not related to differential equations, which is that no matter what the system is, whether it's homogeneous or non-homogeneous, any infinite solution set can be written as a combination of vectors. If it's non-homogeneous, you'll have a particular solution, a vector by itself not being multiplied by anything. In the homogeneous case, all of the vectors will be being multiplied by a free variable.